just by way of introduction, I'm Maya Mathur. I'm an assistant professor at the Quantitative Sciences unit at Stanford University, and my work focuses on, in particular, the connection between meta-analysis methods and causal inference, as well as analyses of replication studies. So today we'll be focusing on the causal inference direction. And so my focus today is going to be on meta-analyses that address causal questions, not questions merely of associations. I'm hearing some music in the background. Is that the Zoom or? Okay, perfect. I think we're good now. Okay, so typically studies that can randomize the exposure usually give us the strongest evidence for causation. But of course, for many types of questions, it's not ethical or feasible to randomize. And in non-randomized studies, any association that we observe between the exposure and outcome might not be causal, right? It could be biased by uncontrolled confounding variables. And the term confounding is sometimes used kind of loosely to mean any form of internal bias. I'm going to be describing confounding today in a more precise way as it's used in the causal inference literature. Specifically, confounders are variables that affect both the exposure and the outcome in a study, and hence potentially produce a spurious association. And in any given individual study, one way to eliminate bias from confounding is to measure confounding variables before the exposure occurred and statistically control for them. We can do this in any number of different ways. For example, adjust for the variables in regression, or restrict analysis to subsets of participants who have the same values of the confounders, use propensity score methods, or many other means. The other thing that's really important for doing causal inference is to have a clear temporal ordering in the study where the confounders are measured first, then the exposure is measured, and then the outcome. Why? Because if the exposure doesn't precede the outcome, we don't necessarily know that we don't just have reverse causation. And the confounders need to also occur before the exposure and outcome so that we know it's not a mediator, or in other words, a mechanism by which the exposure acts. And so meta-analysts can try to reduce bias due to uncontrolled confounding when we design our inclusion criteria. So, for example, in general, cross-sectional studies typically provide very weak evidence for causation, and that's because there's no temporal ordering of the variables. We don't know that the exposure precedes the outcome. We don't know when the confounders occurred. So generally, unless we're in very specific settings where it's clear by virtue of what the exposure and outcome are, what their ordering is. So for example, let's say the exposure is a genetic variant that's fixed at birth, then we know that has to happen before any other outcomes in someone's life, for example. Or if the outcome is mortality, then that is the last thing that happens to someone. And so that is sort of the temporally last thing. But barring these kinds of specific settings, generally cross-sectional studies provide such little evidence for causation that it's probably a good idea to just exclude them in the inclusion criteria for meta-analyses of causal questions. So as a default starting point, we might include only randomized studies, if there are any, plus longitudinal non-randomized studies that have a clear temporal ordering in which the exposure is measured before the outcome and confounders are measured prior to the exposure and are controlled for an analysis. Of course, sometimes we don't know how many studies of different design qualities we'll get, and so sometimes it makes sense to stipulate that we'll include studies with weaker designs, but they'll only be analyzed in secondary analyses, for example. Okay, so we can do our best with inclusion criteria, but of course we're kind of limited by what studies we actually find in the literature. And generally, even strong non-randomized studies are still at some risk of bias due to uncontrolled confounding. So my goal today is to discuss how we might quantitatively assess the strength of evidence for causation in meta-analyses of non-randomized studies that might be subject to uncontrolled confounding. And there's a number of methods to do this. They're generally called sensitivity analyses. And the ones I'll focus on today try to get at this by answering the question, how severe would uncontrolled confounding have to be in order to explain away the results of the meta-analysis in a way that I'll formalize later. And in particular, the methods we'll consider address this question in a way that doesn't require us to know anything specific about the uncontrolled confounder. So we don't need to have, for example, knowledge of the prevalence or the distribution or characteristics like that. Okay, so we're going to start with a single study, and we're going to look at methods based on what's called the E-value in epidemiology. And then we're going to see how those can be generalized and moved to the context of meta-analysis. Okay, so let's consider as an example research on the association of benzodiazepine use in the long term and dementia. And so the question of whether this is a causal, whether associations between benzodiazepine use and dementia is causal has been pretty contentious, in particular because of the potential for uncontrolled confounding. So, for example, some investigators have been concerned about confounding by variables like preclinical dementia, which is pretty hard to measure. So why is that a problem? Well, it could be that preclinical dementia and related symptoms, like let's say sleep disturbances or mood dysregulation, could cause a patient to take benzodiazepines. And so that means that preclinical dementia is something that might affect who gets the exposure. So that's in this diagram, in this causal diagram, that's represented by the arrow going from preclinical dementia to benzodiazepines. And also, probably preclinical dementia could progress to later full-scale dementia. And so that means that preclinical dementia is also a variable that could affect the outcome. So given those two criteria, that means that preclinical dementia could be a confounder. And so if we're not able to measure and statistically control for it in a non-randomized study, we might get a spurious association between benzodiazepines and clinical dementia due to confounding by this variable. Okay, so what I just kind of illustrated is that the strength of these red arrows, in other words, the association between unmeasured confounders and the exposure, and second, the association between unmeasured confounders and the outcome, is basically what controls the severity of bias due to not measuring and controlling for this variable. And so that brings us to the first sensitivity analysis we'll see for a single study, which is called the E-value. And it starts by saying, okay, we're going to think about the strength of confounding as what's called confounding risk ratios. That is the strength of association on the risk ratio scale that uncontrolled confounders have jointly with the exposure and or the outcome. So what do I mean? This red arrow here between the uncontrolled confounder and the exposure, if we were to measure this on the risk ratio scale, that would be one of the confounding risk ratios. And the second red arrow linking the unmeasured confounder to the outcome would be another confounding risk ratio. So two strengths of association. These confounding risk ratios can be interpreted conditional on any measured confounders. And so if we have a study that controls for some other confounders, then we can interpret the strength of confounding risk ratio as sort of above and beyond what's already been controlled. So the E-value is then the minimum confounding risk ratios that uncontrolled confounders would need to have with both the exposure and the outcome, so joint association, in order to fully explain away the observed effect, meaning that there is actually no causal effect and all of it is spurious due to uncontrolled confounding. And if we have an effect size for our study on the risk ratio scale, then the e-value is just a simple transformation of that point estimate. It turns out to be just the risk ratio plus the square root of the risk ratio times itself minus 1. And that is for a risk ratio that's greater than 1. If instead the risk ratio were less than 1, we would take its inverse, and then we would apply the same formula. So the point of this is that if we were to get a large e-value, that would suggest that it would take relatively severe uncontrolled confounding to explain away the effect, and hence that it's relatively robust to uncontrolled confounding. On the other hand, if we got a small e-value, that would suggest that in fact, relatively weak uncontrolled confounding might be able to explain away the effect, and so perhaps it's not very robust. I mentioned earlier that we're not needing to make any assumptions on the actual nature of the uncontrolled confounders themselves. I won't say a whole lot about this, but the reason for my saying that is that the e-value is essentially based on a conservative bound such that it considers essentially worst case confounders with kind of a worst case distribution of prevalences and a worst case distribution across levels of the exposure. And so it's conservative in that it's basically saying, let's consider worst case confounding. Now, if we knew information about, for example, the prevalences, we could potentially get a sharper, more specific bound, but the e-value is saying let's not make any assumptions about what the confounders are. In practice, it's also useful to report an e-value for the confidence interval, which is representing the minimum strengths of confounding risk ratios that uncontrolled confounders would need to have jointly with both the exposure and the outcome to shift the confidence interval to include the null. So the first e-value we saw was to shift the point estimate to the null. This one is to shift the confidence interval to include the null. And so it's basically getting an inferential uncertainty in addition to the point estimate. And in practice, we can calculate an e-value like that simply by applying the existing formula that you saw, risk ratio plus square root of risk ratio times itself minus 1, to the confidence interval limit that's closer to the null. Okay, let's see it in practice. So one large longitudinal study on the question of benzodiazepine effects on dementia looked at about 1,000 older adults and adjusted pretty scrupulously for a lot of pre-exposure confounders. And they got a risk ratio of about 1.38, so sort of moderate increase in dementia incidence with long-term benzodiazepine use, with a confidence interval from 1.05 to 1.81. Okay, so how robust is this to potential uncontrolled confounding? So let's see what the e-values would tell us. So we could calculate an e-value for the point estimate by just taking our risk ratio of 1.38 and applying the e-value formula, and we would get an e-value of 2.11. We could likewise do the same thing with the lower confidence interval limit, which was 1.05. And we would get an e-value for the confidence interval limit of 1.30. Okay, so what would we conclude in practice? So this paragraph is kind of designed to be something that could be used relatively as a template for kind of reporting e-values in different analyses. So this might be what we would write in our journal article. With an observed risk ratio of 1.38, uncontrolled confounders that were associated with both benzodiazepine use and dementia by a risk ratio of 2.11-fold each, above and beyond any measured confounders, could potentially explain away the estimate. But jointly weaker confounding associations could not. And furthermore, uncontrolled confounders that were associated with both benzodiazepine use and dementia by risk ratios of 1.3 each, again, above and beyond any measured confounders, could shift the confidence interval to include the null. But again, weaker confounding could not. And so in practice, we would then want to think about what these e-values mean in the context of the quality of the study design. How well did the study actually control for existing confounders? How clear was the temporal ordering of the exposure and the outcome? And we would then use this information to think about whether it's plausible or not plausible that there actually could have been uncontrolled confounders that were this strongly associated with both the exposure and the outcome. And that would inform our judgment of how robust this evidence is. Okay, let me pause now and see if there are any questions about individual studies before we see how it translates to meta-analyses. I think I see one thing in the chat, so we'll see what that is. Oh, follow us on Twitter. Cool. And yeah, folks are free to also just unmute yourselves if you prefer to just say it out loud. But we'll certainly stop at the end for questions as well.
I can read the question. There's a question by Wolfgang. So you assume that the confounding RRs are both the same?
Okay, this is a great question. So it's not an assumption, but rather a conservative setup in that basically if you want to jointly minimize both of the confounding risk ratios, then you end up in a setting where they're the same. And so it is true that the e-value is characterizing risk ratios that are equal. It's not an assumption in that it's basically saying, what is the joint minimum? Let's try to be as conservative as possible, given that we're not assuming anything about which risk ratio is larger, and then find the joint minimum. It does bring up an important point, though, which is that sometimes we're in a setting where we actually do have some information about the confounder, especially if we're doing an individual study rather than a meta-analysis. Perhaps we actually think, oh, I actually know something about the prevalence of one of these, or I know I have a specific confounder in mind. And those are settings where we might want to apply a more a sensitivity analysis that has more parameters involved. Now, it does involve making assumptions. If we do that, it's potentially less conservative, but that is a way to get a sharper bound. Great. Okay, so let's take a look at how this would apply to meta-analyses. Just to kind of point out the references here, this is kind of the main statistics paper that proposes the methods, some more robust versions, and then a review paper that kind of goes through a tutorial for how to apply them in practice. Okay, so we're going to consider an example that has been very, very spicy, which is meta-analyses on whether being overweight versus normal weight is protective with respect to all-cause mortality or detrimental. And so there's been in particular kind of two meta-analyses that have been at war with each other. There was first one in JAMA by Catherine Flegel et al., which suggested an average beneficial effect of being overweight versus normal weight on all-cause mortality. Pretty small effect, but protective, so hazard ratio of 0.94 with a 95% confidence interval bounded below 0.96. Okay, so that's interesting. Then another group later published an IPD meta-analysis, individual participant data, which actually instead suggested an average detrimental effect of being overweight. Still a relatively small effect size, hazard ratio of 1.11 with a confidence interval from 1.1 to 1.11. But this sparked a war, which has been going on for quite a while. With some very actually quite personal attacks and just a lot of really, really strong opinions on both sides. But I think one thing that has been maybe not received that much attention in this debate is that I think both of these meta-analyses are potentially subject to quite a bit of uncontrolled confounding. So most of the studies that were analyzed, or actually all of the studies in the case of the latter meta-analysis by the Global BMI Mortality Collaboration, adjusted for some confounders, but certainly not all of the ones that seem important. So most or all studies, depending on the meta-analysis, did not adjust for socioeconomic status, physical activity, anything about diet, baseline body mass index, and other possible confounders. Again, why be concerned about these? Because these are variables that seem like they could plausibly affect someone's BMI and also independently affect their mortality. So given this, how might we characterize sensitivity to uncontrolled confounding in these meta-analyses? Okay, so the current, I guess one important component of current standard practice, for example, as required in Cochrane reviews, is the grade approach. And this starts by kind of heuristically gauging the proportion of information in a meta-analysis that's contributed by studies at lower versus higher risk of bias. And this is based on, this is not necessarily a quantitative proportion of information, but kind of a heuristic judgment of the relative weight of these different studies. And then to use this information to decide whether to downgrade the overall certainty rating for the meta-analysis from the default of high certainty to something lower, moderate, low, or very low. And we can then also optionally choose to upgrade the rating again if, for example, we have a pretty strong pooled estimate, like, for example, grades suggests a criterion of risk ratio greater than 2 or less than 0.5. And this definitely has strengths, but it also has some limitations as well. So I think one is that it can be hard to intuit how much sort of information each study contributes to the meta-analysis when studies' estimates and precisions differ. And deciding how to downgrade or upgrade the overall certainty rating can be fairly subjective and also fairly qualitative. It's not really giving us a quantitative summary of how the numerical estimates might actually have been affected by bias. And so I think this is certainly useful, but I do think there's also room to additionally add quantitative sensitivity analyses to supplement an approach like this. And to do that, we're going to look at some analogs to the e-value that apply to meta-analyses. Okay, I see a couple of things in the chat, so let me pause and see what questions there are. Okay, great. So this is, okay, great. Also, with respect to papers, there was a question in the chat about this. The slide deck will be publicly available. It actually already is. There's a link at the end for how to download it. That has the full reference list along with full citations. Okay, so let's look at e-values for meta-analyses. And we're going to look at a couple different flavors. The first thing we're going to look at is what happens if we just apply the e-value to the pooled estimate of our meta-analysis. Can we do that, and what does it mean? And the answer is yes. Yay, we can do that. And what it represents is the average confounding risk ratios across studies that uncontrolled confounders would need to have with studies' exposures and outcomes in order to shift the pooled estimate, let's call it mu hat, to the null. Okay, so note that I'm saying average confounding risk ratios because just as we can have genuine heterogeneity and population effects in meta-analyses, we could also have heterogeneous bias, right? We could have different confounders in different studies. We could have some studies more fully adjusted than others. We could have different strengths of associations of the same confounders based on different populations or different study designs, for example. So kind of two different flavors of heterogeneity. And so again, so this e-value is talking about the average strength of these confounding risk ratios across studies that would be needed to essentially explain away the pooled estimate in our meta-analysis. So let's go back to the meta-analyses on overweight and mortality and see what we get by applying e-values to them. So for Flegel, that was the one that was indicating a protective association. We get an e-value of 1.36. So again, saying that if across studies on average, there were uncontrolled confounders that were associated with both being overweight and mortality by risk ratios of 1.36, that could potentially be enough to explain away this protective association. And similarly, for GBMC, the meta-analysis that indicated a detrimental association, we get an e-value of 1.43. So kind of comparable strengths of confounding. E-values to shift each confidence interval for the pool estimate to include the null were 1.25 for Flegel and 1.36 for GBMC. So that's kind of interesting. I think given the relatively limited control of confounding in these studies, it seems to me relatively plausible that there could be this amount of residual confounding, again, by factors like socioeconomic status or diet or physical activity. And so that's interesting. And we also see, relatively comparable e-values for these two meta-analyses. Okay, so a little bit more detail on this e-value for the point estimate mu hat. It doesn't require making assumptions on the distribution of the population causal effects or assumptions on the distribution of bias across studies under two assumptions. So first assumption is basically the meta-analysis of the confounded effects needs to be correctly specified in the sense that we need to fulfill any distributional assumptions of the model that we're fitting. So in particular, it could be the case that the population confounded effects are non-normal, even if maybe the causal population effects are normal. Why? Because the confounded effects are basically a function of both the true causal population effects as well as the bias. And if it happens that the bias is not normal or distributed in a certain, in a different way across studies, we might end up with non-normal confounded effects. And so, this is not really saying all that much other than we can't fit a meta-analysis method that assumes normality to confounded effects that aren't normal and then interpret the results. The second assumption is that the bias in each study is independent of its population causal effect and also its standard error. So this is important in that, we can't be in a situation, for example, where it's specifically the smallest studies that are the least biased, for example, or a situation where studies with larger true causal effects are more or less biased. Note that this is not talking about independence from the confounded effect. Of course, the bias is going to be associated with the confounded effect because more bias is going to be associated with a more spuriously inflated confounded effect. Okay, so it's sort of good news that we can apply the e-value directly to the point estimate and get something that's interpretable. It does have some limitations. In particular, it is describing the evidence strength in a meta-analysis only in terms of the pooled point estimate and its confidence interval. And as many have argued, in addition to the pooled point estimate, it's good to more holistically describe the potentially heterogeneous distribution of effects in a meta-analysis. And in the literature, there have been various ways to do this, right? There have been prediction intervals. That's been a nice one. And there are other metrics as well that we'll consider as targets of sensitivity analyses. So, for example, by choosing a metric that helps summarize the heterogeneous distribution of effects, we could then conduct sensitivity analyses that ask how much confounding it would take to explain away that alternative metric of evidence strength. Let me pause again for questions on the e-value for mu hat before we move on.
question from James. Can you say more about the assumption re-independence of bias in SE?
Mhm. Yeah. So we can't be in a situation where, for example, it's on average, the larger studies, let's say the ones with smaller standard errors, have systematically more or less bias than smaller studies. That would be a problem for methods that essentially do sensitivity analysis for the meta-analysis holistically rather than individually adjusting each study. Now, if we were in a situation where we thought we had a correlation like that, we could do some kind of sort of modeling of the whole meta-analysis where we, let's say, maybe have some sort of Bayesian prior on the correlation between the standard errors and the bias. But if we're just going to kind of operate on the meta-analysis as a whole and consider kind of basically like a location shift and a scale shift representing the effective bias, then we can't have the bias correlated with either the standard errors or the population causal effects.
Yeah, can I ask you another question?
Yeah.
Can you comment on whether or the extent to which this logic is contingent on the using the risk ratio scale as opposed to other metrics?
Yeah. So basically, for both individual studies and meta-analyses, what we would do if we had an effect size on some other scale is first approximately convert it to a risk ratio, and then use that converted effect size when calculating the e-value itself. We could alternatively do analyses on kind of the native scale where we basically look at the multiplicative bias that would be required in each study, but the conversion from multiplicative bias to confounding strengths requires being on the risk ratio scale. But so essentially if we had, let's say, a standardized mean difference, we'd convert it to a risk ratio. I'll show later a slide with software that does that automatically, and we would then do the sensitivity analysis on the risk ratio scale. Okay, so let's look at a second e-value analog for meta-analyses that gives us a more holistic picture of the distribution of heterogeneous effects. Okay, so one approach to sort of in addition to measures like prediction intervals to characterizing the distribution of population effects in a meta-analysis is to look at the proportion of what we might call meaningfully strong effects. So the idea here is to choose in scientific context a threshold that represents what we might consider a meaningfully strong effect size. For example, maybe in the context of, let's say, potentially detrimental effects of being overweight on mortality, maybe we would say, well, if the hazard ratio isn't stronger than 1.1, for example, maybe that's kind of too weak for us to really care about. We can then estimate the proportion of population effects that are stronger than that threshold. And that is basically a metric of kind of how much of this potentially heterogeneous distribution represents meaningfully strong effect sizes. We could also estimate and report the proportion of population effects that are below some threshold on the other side of the null. So maybe we'll say, perhaps for protective effects of being overweight on mortality, maybe they need to be stronger than a hazard ratio of 0.90 in order to be meaningfully strong. So how many effects are in that lower tail? And all of this holds whether we're in the context of sensitivity analysis or not. These metrics could be reported in general for random effects meta-analyses. And the point of looking at metrics like this, in addition to just the point estimate itself, is that they can help identify situations where, for example, maybe the pooled estimate is significant, but there actually aren't very many meaningfully strong effects because maybe the meta-analysis mean is fairly small. Maybe there's not very much heterogeneity. Maybe there are a lot of studies, so it's significant, but there's actually the effect sizes are not that large. Or alternatively, maybe the meta-analysis mean is close to the null, but there's enough heterogeneity that there actually are some fairly strong effects in the tails. Or finally, that maybe there's enough heterogeneity that it's also fairly common to have strong effects in the direction opposite the meta-analytic mean. And in these latter two scenarios, this would also probably point us towards the need to kind of delve more deeply into causes of the heterogeneity, kind of what is driving the heterogeneity in these effects. And so again, just in the general context of random effects meta-analysis before considering confounding, these proportions can be estimated using preferably robust non-parametric procedures, which are essentially based on shrinking studies' point estimates towards the mean. So it's sort of conceptually similar to an empirical Bayes estimate, where you're kind of shrinking the estimates to account for their over dispersion relative to the true population effects that is due to the statistical error. Or we can use simple parametric estimates and inference, which I'm showing here because they're kind of more clear to look at. And so, I mean, the parametric version is very straightforward. It's basically just saying, well, the estimated proportion of effects that are stronger than Q, if we assume that the population effects are normal, is essentially just kind of the appropriate tail of a normal distribution whose mean is the mu hat from our meta-analysis and whose heterogeneity is tau hat, the estimated standard deviation of population effects. And similarly for the proportion of effects that are less than some other threshold Q star, we can just look at the lower tail of the appropriate fitted normal distribution. This is implemented in an R package called Meta-Utility if you want to try playing with this. Okay, so let's look back to the two meta-analyses on BMI. Again, this is prior to considering confounding. So what I'm plotting here in the black curve is an estimated smoothed density of the population hazard ratios in each meta-analysis. And so these are, again, not the point estimates, but rather these are the estimates that have been appropriately shrunken towards the mean. And the gray line is the null hazard ratio of 1. And so you can see that there's a fair bit of heterogeneity in both of these meta-analyses. And Flegel et al., certainly the majority are protective, but there's also a decent number that are in the detrimental direction. And for GBMC, a larger majority are detrimental, but still decent amount of heterogeneity. And I've marked in red here the two thresholds that we'll be primarily considering as defining meaningfully strong effect sizes. So hazard ratios of less than 0.9 for being meaningfully protective, and hazard ratios of greater than 1.1 for being meaningfully detrimental. So again, prior to considering confounding, if we estimate the percentage of studies with meaningfully strong protective effects in each meta-analysis, we get about 40% in Flegel, but 0% in GBMC. And conversely, if we estimate the percentage of studies with meaningfully strong detrimental effects in each meta-analysis, we get about 9% in Flegel, but 50% in GBMC. Okay, so that seems like pretty a different picture from these two meta-analyses, and that we do seem to have a pretty clear difference where Flegel's meta-analysis is really largely detrimental effects, and GBMC's is protective, and GBMC's is largely detrimental. Okay, so now what if we consider the possible effects of confounding? So let's do an analog to the e-value now that is considering this proportion of meaningfully strong effects, p hat, instead of the pooled point estimate, mu hat. And the rationale is that when effects are heterogeneous across studies, we might define explaining away the results of the meta-analysis in terms of substantially reducing the proportion of meaningfully strong effects. right now, we're going to consider bias that is homogeneous across studies, meaning it's of the same strength in all the studies in the meta-analysis. We'll change that later. Okay, so second e-value analog that we'll see today is a metric called G hat of R and Q. And this is the minimum confounding risk ratios that uncontrolled confounders would need to have with both the exposure and the outcome in each study in order to reduce to less than R, let's say 15%, the proportion of studies with causal population effects that are meaningfully strong. And so considering the two example meta-analyses, let's say we wanted to reduce the percentage of meaningfully strong protective hazard ratios in Flegel to 15%. And we wanted to reduce the percentage of meaningfully strong detrimental hazard ratios in GBMC also to only 15%. So in other words, to kind of have both meta-analyses be sufficiently confounded that they're not really providing very strong evidence for meaningfully strong effects in the direction that is the pooled point estimate for that meta-analysis. And so for Flegel, we would get an e-value of 1.43. So again, if each study in Flegel had confounding risk ratios of 1.43 with both the exposure and the outcome, that could be enough to reduce to only 15% the proportion of meaningfully strong effects. And in GBMC, we get confounding risk ratios of 1.1. So actually kind of even less robustness. And so that was considering kind of one particular numerical summary. So it's saying, let's consider specifically reducing the percentage of meaningfully strong effect sizes to 15%. But we could also look at this more continuously. What we could do, for example, is plot the strength of confounding risk ratios in each study for each meta-analysis and consider the effect that that has on the estimated proportion of meaningfully strong effect sizes. So this left-hand panel here is for Flegel. And so you can see, for example, the leftmost cross-section here is basically when there's no bias in any study, right? Because the confounding risk ratio is 1.00 in each study. And so this 40% is actually what we got in the initial analysis where we were assuming that there was no confounding. And then as we get more and more confounding in each study, of course, we get fewer and fewer meaningfully strong population effect sizes. Likewise for GBMC, the naive estimate was around 0.5 and then declines as we have increasing confounding. Just as an aside, this lower axis is a different way to think about the strength of confounding, and it's referring to basically the multiplicative bias in each study. And so that is kind of prior to considering the risk ratios that a confounder would at minimum need to have to produce that amount of bias. So those analyses considered bias of homogeneous strength across studies, right? So every study has the same amount of confounding bias across the board. In some settings, depending on the choice of threshold relative to the pooled estimate, this turns out to be statistically conservative in the sense that the meta-analysis would only look more robust or less robust depending on the direction of argument that we're trying to make. And so in some settings, it's useful to do this because it's kind of a conservative estimate of what we're trying to look at. But I think it's also good practice to additionally consider bias that is heterogeneous across studies. And so for these particular meta-analyses, we also did analyses where we considered bias that was log normal across studies and that accounted for 80% of the total estimated between study variance. So what do I mean by that? When we estimate tau squared, the variance of population effects in a confounded meta-analysis, what we're getting is a combination of the true heterogeneity in the population causal effects as well as the heterogeneity in the bias. And so the idea here is let's consider bias that's really quite heterogeneous, such that it actually accounted for 80% of the observed between study variance. And so we did analyses like that, and we ended up with quite similar conclusions, albeit with some increase in uncertainty. So kind of overall conclusions for these two meta-analyses, basically we found that confounding risk ratios of only 1.25 to 1.43 in each study could shift mu hat or its confidence interval to the null, or alternatively to substantially reduce the proportion of meaningfully strong effects to only 15%. And again, it's critical to try to interpret this in light of the quality of control of confounding in these studies. And I think in this case, given relatively limited control of confounding by probable physical, social, behavioral, and psychological factors, I think arguably these results suggest that ultimately neither meta-analysis really provides much evidence for effects in either direction, protective or detrimental. It's a little bit puzzling that it feels like there's been kind of quite a war about these meta-analyses where really, arguably there's kind of a major limitation in just what we can actually conclude from either of these, given both the relatively small point estimates at the outset and the limited control of confounding that these studies have. And so I think if we're going to try to establish credibly potentially quite small effects in either direction of being overweight on mortality, this is really going to require improved primary study designs as well as meta-analyses as well. Okay, so there's software available to do all of the analyses I mentioned. So the R package eValue will handle both individual studies and meta-analyses using the function confounded meta. There's also a web interface, evaluecalculator.com/meta, which will do basically the same things as the R package, but with a point and click interface. There's a detailed tutorial with kind of screenshots walking you through both the website and the R package in this 2022 paper, if you're interested in that as well. Okay, so a few concluding remarks. So I focused today primarily on quantitative sensitivity analyses for that you do kind of after you've conducted a meta-analysis, but I certainly don't want to give the impression that that's the be-all and end-all of addressing confounding or indeed other within study biases and meta-analyses. So in this review paper, we also gave some other recommendations, and certainly other groups like Cochrane have given some great recommendations as well. So for example, we suggest kind of pre-specifying inclusion criteria that reduce risks of bias. As I noted earlier, I think that by default, meta-analyses considering causal questions should generally exclude cross-sectional studies. To pre-specify which types of study designs will be included in primary versus secondary analyses based on the strength of evidence for causation that they provide, and to stratify analyses on designs that provide substantially different levels of evidence. Certainly, it's also good to qualitatively characterize risks of bias using existing tools. There's many good ones out there. Robbins 1 is great for non-randomized studies, as well as other summaries we suggest of kind of the proportion of studies that have different sort of levels of design in terms of longitudinal structures. And finally, this is the piece we focused on today, kind of quantitatively assessing sensitivity to residual biases and interpreting those results in light of the qualitative risk of bias assessment. So again, I'm not proposing that these analyses be done instead of any of these other steps, but rather this is an additional step that I hope will also be useful to meta-analysts going forward. So in summary, confounding bias, as well as indeed other within study biases in the synthesized studies, can propagate to meta-analysis estimates. And so in addition to trying to limit bias through carefully chosen inclusion criteria and applying existing rating tools to characterize individual studies, I think it's also helpful to more holistically characterize the robustness of the overall meta-analysis results to possible confounding. And we saw methods that are analogous to the e-value for individual studies that are relatively straightforward to apply in practice and sort of require relatively little knowledge about what the confounders actually are. And sometimes, as we saw in the applied example today, sometimes these analyses suggest that uncontrolled confounding is actually a pretty serious threat to the credibility of a meta-analysis estimate. But other times they suggest the opposite, especially if we have a pretty large point estimate for the meta-analysis, as well as fairly well-controlled studies that are being synthesized. So I will leave us here and take questions, but the slide deck, as promised, is posted online, including a reference list, and there's my email address if you want to reach out later. So happy now to take any further questions. Let's head over to the chat.
Happy to take questions. You can also feel free to unmute yourself if you want to chat vocally. Maya, can you say anything about, so I think your last couple of slides addressed this a bit, but the thing that I could see people being uneasy about with the e-value for meta-analysis is just that it seems like you're often in a situation where studies have heterogeneous risk of bias. And so it seems like the logic of the e-value is to kind of penalize every study equally, right? You're like, assume there's like a assumption about like a homogeneous, so like additive shift, or the bias is creating a homogeneous additive shift in the log risk ratio. So I guess, do you have any like response to that critique? Like, what if you're in a situation where you've got like 2 really well-controlled trials, or even RCTs, right? Plus like a dozen observational studies, some of which are good, maybe because you did them, and others of which are not very strong and that don't account for as many important confounding factors. Like, what do you do in a situation like that?
Yeah, I love it. Okay, so that's a setting, that's a very interesting setting, and one that certainly happens where we have both RCTs and observational studies. And so there's actually, in the reference list, we show in the supplement of, let's see, it's a paper in epidemiology. It's this one. This paper here goes through that exact setting. So yeah, what do you do if you actually know in more detail which studies are maybe unbiased because they're RCTs, at least with respect to confounding? And so yeah, so you certainly can handle situations like that. So the versions I showed here, I would say are most useful in contexts where we think the bias might be heterogeneous across studies. We can accommodate that, but we don't necessarily feel comfortable specifying for each individual study how biased it is. There are also, perhaps because we don't necessarily know, maybe we have some sense of the overall biases in this literature, but we don't necessarily have a setting where there are clearly kind of a handful of RCTs and then a handful of kind of much worse studies, for example. Yeah. I do also comment in the review.
Every study of diet or food consumption ever.
Right. Yes. Exactly. Yeah. And then in the 2022 annual review paper, we do also review a lot of other methods for quantitative sensitivity analysis, some of which will work well if you have a very specific understanding or guess about how much bias is in each study. I mean, the caveat, of course, is kind of, we don't necessarily have that much information, and you do end up with kind of a proliferation of sensitivity parameters like for each study. And so you end up with a lot of things to specify. But I do think that the more precise knowledge we have, the more it makes sense to kind of do additionally more precise sensitivity analyses as well.
Okay, yeah, great, thank you.
Okay, for computing the proportion of meaningful effects, did you use the estimates of mu and tau and assume normality as shown on one slide, or are you using the distribution of BLUFs, which is best linear unbiased predictors, as you showed on the other slide? I got lost in that part. Yeah, okay, so great question. So the results I showed for homogeneous bias are using the BLUFs, which are, we call them kind of calibrated estimates, the ones that are shrunken towards the mean. For heterogeneous bias, you end up needing to specify, make some assumption on the distribution of the bias. And so that is using the parametric estimates. I didn't show the actual form of the parametric estimates under confounding, but that's available in the references. Have you considered the differences among individual studies in modeling approaches to make causal inference, like propensity score, instrumental variables, or does it matter? Yeah, great question. So it matters only insofar as different methods, especially depending on their different assumptions and how well those are fulfilled, could produce an ultimate estimate that has a different amount of confounding. And so if you have heterogeneity across studies and how they model confounding, including both what variables they use and what methods they use, that could produce more heterogeneity in the bias across studies. But it doesn't matter insofar as, I mean, in principle, any of those methods has a sort of a valid set of assumptions under which it will work. And it's basically that there's no unmeasured confounding in all of these cases. And so insofar as the methods are applied correctly, they will kind of produce an unbiased literature if all of the confounders are measured, which is kind of the problem that we're considering.
We are right at the hour, so I can stick around for another couple minutes if folks want to keep chatting, but before we do that, I'd just like to thank our speaker, Dr. Maya Mathur, one more time. Really interesting work and a crystal clear presentation of it as well. Thank you very much.
Thank you so much for having me. A pleasure.
And for the SIG members, our AERA convention is coming up next week. Look for an email from the SIG leadership team early next week about the program at the convention. We've got a really extensive and varied program, including both online talks and in-person sessions if you are headed to San Diego. If you are headed to San Diego, also note our business meeting is next Monday evening. That's April 25th. And we will have facility to connect to that online as well if you're not traveling. If you are traveling, hope to see you there. Come give us a like an elbow knock or whatever. And thanks all very much for coming. This concludes our the spring seminar series of for the SIG. We are in the process of getting speakers together for the fall as well. So if you're interested in presenting or have suggestions for speakers you'd like to see, feel free to reach out to me. Okay, thanks everyone for coming. Take care.
Thanks everyone.